recording at this point. So thank you all for attending this third spring quarter Applied PV seminar at the University of Washington. The speaker today is our own Ryan Creedon. Ryan finished his PhD from this department 1 year ago, and he will tell us about the work that he did in that thesis, and including maybe some new results. And then if anybody has any questions, I believe Ryan's okay with questions during the talk. So you can unmute yourself and ask, or you can also put them in the chat, whichever you prefer. We'll also have questions after the talk, at which point we will no longer record. So without further ado, Ryan, go ahead.
Well, thank you so much, Bernard, and thanks, Anastasia, for setting up the Zoom session and putting in all the upfront work to make sure that we could all be here today. It's really my pleasure to give one of these seminar talks. I've sat through many of them myself and have taken a lot of inspiration from them, and I hope that I can, in some way, shape, or form, return the favor. Today, I am going to be talking a lot about what my recent PhD thesis was about, and I'm hoping that you're going to find, as the audience, a lot of connections between what were in the last two talks about the rigorous results for the Benjamin-Feir instability and what we're going to talk about today. So our story really starts with the Stokes waves, just like in the previous seminar talks. And as you can see here, I don't have quite as nice a photograph as maybe was used in some of the previous talks, but hey, this still gets the point across. A Stokes wave is a solution of Euler's equations that essentially is a small amplitude periodic traveling wave solution. And the basic sort of punchline to these Stokes waves is that they travel in one particular direction. Hopefully you can sort of see my cursor here. I don't have one of those little fancy tracking ones, but they travel in one direction. And in the transverse direction of that propagation direction, there's very little variation in the shape of these waves. And so these are going to be the object of focus in this particular talk. And in particular, what we're going to be very interested in is a question that is now 70 years old. And that question is, are these Stokes wave solutions stable? And really what I mean by this, and what folks back in the 60s who were looking at this problem, how they thought about the problem, was you take a Stokes wave profile, which here is this blue sort of sinusoidal looking wave, and you perturb it just right. And so maybe those perturbations are relatively small. And so we get something like this red curve right here. And the question is, what happens to this slightly perturbed wave profile as you start evolving time? And what folks back in the 1960s discovered, particularly Benjamin-Feir, Whittam, Zakharov, a couple other folks, realized was that actually, if you perturb these Stokes waves just right in sufficiently deep water, then your wave profile in red actually doesn't come back to the Stokes wave solution. It turns into something else. In fact, the amplitude of this wave ends up getting modulated, and you get these beat-like structures to your solutions. And so even in the 1960s, people were starting to come around to the idea that, in fact, Stokes waves aren't stable. They have this modulational instability to them, where the envelope of our wave packet starts to modulate. And today, we usually refer to this modulational instability as the Benjamin-Feir instability to pay homage to the original wave tank experiments that were done in the 1960s by Benjamin and Feir. And that was sort of talked about in, I believe, the very first talk of this seminar series. So I won't go too thick into the weeds about those initial experiments by Benjamin and Feir. Instead, what I want to show you is just a history of what's happened since the 1960s. And this is by no means a comprehensive history. You can think of these papers as essentially like the greatest hits of the last 7 decades, specifically in reference to Stokes waves in the pure gravity case. So we're not talking about the complicating factors of adding surface tension. We're not going to talk about adding viscosity and all of those extra complicating factors. These papers directly address Stokes waves, and in particular, their stability in the pure gravity case. And it's very interesting to look back at this history because you'll notice a lot of interesting trends. First off, in the 1960s, the main method of analysis was really asymptotic analysis, formal asymptotic analysis. And that's really because in the 1960s, rigorous analysis wasn't yet ready to tackle this problem. As you're going to see a little bit later on, there's a lot of complicating factors here. And also computers weren't quite up to the task of helping us to really see what these unstable Stokes waves look like. But you can see as we sort of move into the machine age here, into the 70s, 80s, 90s, 2000s, that all of a sudden we get a bunch of numerical results that are popping up about the stability of Stokes waves. So these are your papers by Bryant, Longwood-Higgins, McLean, a little bit later on by Karif and collaborators. There's a lot of different numerical results that are out there for the stability of Stokes waves. And peppered into those rigorous results every so often peppered into those numerical results every so often are these rigorous results. The most important one from 30 years ago is this paper by Bridges and Milka that actually proved for the first time the existence of this Benjamin-Feir instability in finite depth. And so outside of really that paper and maybe a few others, there really weren't very many rigorous results out there for this problem. And it's only when you look at the last decade, literally from the time the pandemic started till now, that you see this explosion of rigorous results for this spectral stability problem. And so the question is, what is generating this sort of explosion of rigorous results? And I would argue that it's this picture right here. So what you're looking at is a picture, a plot of a stability spectrum for a chosen Stokes wave of some sufficiently small amplitude in some finite depth. And so this stability spectrum comes from linearizing Euler's equations about the Stokes waves and solving a resulting spectral problem. And the eigenvalues of this spectral problem give us information about the exponential growth rates of the perturbations that we've applied to the Stokes waves. So what we're looking for here in this picture are really eigenvalues that enter the right half complex plane. These correspond to perturbations that grow exponentially fast in time away from the Stokes wave solutions, and therefore give us instability. And so you can see in this plot on the left, these are your eigenvalues. Here's the imaginary axis, here's the real axis. You can see that there are multiple places where we enter the right half complex plane. There's what's happening at the origin, which turns out to have a connected set of eigenvalues that forms this beautiful figure 8 pattern. And then there's stuff that happens away from the origin that creates these little bubbles of instability where we have eigenvalues entering the right half complex plane as well. Now, when I started my PhD thesis, which I can't believe was 7 years ago almost, time really flies when you're having fun solving these wave problems. But when I started this PhD, we didn't have any rigorous results about this picture at all, except for the Bridges and Milka result, which told us that if you get very close to the origin here, you will find an eigenvalue that enters the right half complex plane. So literally in this zoom in right here, this little tiny region where you see these two lines intersect, that's all we knew rigorously. And by the time I was done with my PhD, the amazing thing is in just a 4 or 5 year time window, suddenly we have all of these wonderful rigorous results. Of course, we've seen in the last 2 videos the results of Berti et al. And a little bit of the Wynne and Strauss stuff, although we'll see that a little bit later on in a future talk. But essentially, those works are allowing us to conclude that these eigenvalues that are on this figure 8, they all exist, and they correspond to that much beloved Benjamin-Feir instability, the modulational instability, in other words. And then there's also a preprint that's out, and it's been out for a couple years now, and I'm suspecting that it's in the review process currently, about some rigorous arguments for the existence of this first instability bubble away from the origin, which this type of instability is different than the Benjamin-Feir instability. We call it a high frequency instability. And that is a paper by Her and Yang that, like I said, is a preprint that's been out for a little bit now, but hopefully with any luck, it will get through the peer review process later, and we might actually hear more about it at a later talk in this seminar series. So in that 3 to 4 year time span, suddenly, boom, we understand what's happening at the origin, and we have some understanding of at least what's happening a little bit further away from the origin. But really, when my PhD thesis started, we didn't really have anything. And so here's where sort of my contribution to this storyline comes in. All we had at the beginning were really numerical results. So one of the things that we wanted to try to do, Bernard, myself, and our collaborator, Olga Trchenko, who's now at Western University. So what we wanted to do is obtain asymptotic expansions for these curves, for the Benjamin-Feir instability curve, and also for these high frequency instability bubbles away from the origin. And doing this has a number of pleasant consequences. One of the pleasant side effects is that we will be able to obtain asymptotic expressions for the most unstable eigenvalues on each one of these instability curves. So that will give us insight into what the largest growth rates are for the Benjamin-Feir instability, as well as these high frequency instabilities away from the origin. The other pleasant side effect, which was not necessarily our intention at the outset of this problem, although Bernard, feel free to disagree with me, but we didn't know that all these rigorous results were going to come out at the same time we were working on this problem. But what's incredible about our results is that they connect the rigorous results to the numerical results that we already knew. And so you can kind of think of my contribution to the story as a connecting piece between all of these recent rigorous results that have come out and all of the numerical results that we already know, and really making sure that we're speaking the same language, that those two camps are really talking about the same thing. So my goal by the end of this talk is really threefold. We're going to develop a perturbation method that's going to asymptotically approximate all of these different spectral instabilities in that stability spectrum. And what we're going to get from this perturbation method are three different things. We'll hopefully get some explicit algebraic curves that are asymptotic to these instabilities. From getting those expressions for the algebraic curves that are asymptotic to these instabilities, we can estimate the maximum growth rates of these instabilities. We can then compare the high frequency instabilities and the Benjamin-Feir instability. And as sort of a preview of coming attractions, because I didn't define what this is yet, we will also be able to approximate the interval of Floquet exponents that parameterizes each instability. So I didn't, again, define what Floquet exponent is yet, but we'll get there when we're ready to talk about it. And we will be able to obtain that interval that parameterizes these curves. And that interval is going to give us some information about what types of perturbations do we need to apply to the Stokes waves in order to get these instabilities that we observe in the stability spectrum. So that's the big picture. This is going to be a formal asymptotic analysis that's going to be very much complementary to the rigorous results that you've already heard in this seminar series, as well as some of the rigorous results that you might hear a little bit after this talk happens. And so to sort of ground our analysis here, I'm going to make a deliberate choice on which one of these curves to sort of focus in on and discuss this perturbation method with you. And the particular curve that I'm going to choose is going to start off with this first high frequency instability bubble away from the origin. And if we have time, hopefully I'll be able to show you some results for other high frequency instability bubbles, as well as how you can modify this perturbation method to give you the Benjamin-Feir instability as well. But I'm going to make the choice to focus on the high frequency stuff because we've already had 2 talks about the Benjamin-Feir instability. So I figured we'd do something a little bit different just to break it up for a little bit and give you a little bit of reprieve before we dive back into Benjamin-Feir. So how is this perturbation method going to work for the high frequency instabilities? Well, the first step is you have to choose your favorite formulation of the water wave equations. Now, traditionally as written, the Euler equations are a free boundary value problem. There's a Laplace equation in the interior of your fluid, and then there's a bunch of boundary conditions that tell you how the top interface evolves. And in this case, we're enforcing periodic lateral boundary conditions, no flux conditions at the base of your fluid, all that jazz. Those equations are wonderful as a starting point, but it turns out that for asymptotic analysis, there's an even better starting point, which is the Ablowitz-Fokas-Musslimani Formulation. And so these are the equations governed by the Ablowitz-Fokas-Musslimani Formulation of the water wave equations. The variable Q here is your velocity potential at the free surface, and your variable eta, which is showing up, in here, also in this equation right here and right in here, that's the free surface. And we're assuming that we're just doing a one-dimensional free surface here, simple as possible, with longitudinal perturbations that we're going to apply in just a second. So here's the Ablowitz-Fokas-Musslimani formulation. The first equation we call the local equation, and many of you will recognize that this is just the Bernoulli boundary condition at the top interface. That's essentially all it is. This second equation, which we call the non-local equation, is essentially encoding the Dirichlet-de-Neumann operator, but it's doing it in a way where the Dirichlet-de-Neumann operator is not explicitly in these equations, but it's somehow implicit in these equations, kind of sneaking in the background. If you solved for eta t in this non-local equation, then you would arrive at the famous Dirichlet-Neumann operator equation and the Creedon formulation of the water wave equations. But this formulation turns out to be a little bit friendlier when you want to do asymptotic analysis, because you don't have to expand the Dirichlet-Neumann operator. You can just plug your expansions right in here into the non-local equation. So that's going to be our starting point, is this particular formulation of the water wave equations. And we're already going to move into a traveling frame because we're going to talk about Stokes waves in a second. So anytime you see the x variable from here on out, it's really the variable x minus ct, where c is the velocity of our Stokes waves. And we're also going to non-dimensionalize so that our waves are 2 pi periodic. So the wave number parameter kappa in this case is going to be 1. We're going to set gravity to 1 without loss of generality. And we're going to send our dimension depth parameter h to a dimensionless depth parameter, which we're going to call alpha. And that's going to be given by the dimensional kappa value times the dimensional depth value. So if you choose this starting point for your formulation of the water wave equations, and you do some non-dimensionalization and you move to a traveling frame, your next step is to calculate the Stokes waves. This is a very classic calculation. If you go to Whittam's textbook, you can go to like chapter, I think it's 7 or 8, and he fully derives how you calculate the Stokes wave expansions from a formal asymptotic analysis perspective. The basic idea is we're going to take the surface wave profile and expand it in a small parameter, which we're calling epsilon. Epsilon is essentially going to be keeping track of the amplitude of our waves. It's a parameter that scales with the amplitude of our waves in this non-dimensional setting. And then we're also going to have to expand our velocity potential at the surface. And because this perturbation method is essentially a Poincare-Lindstedt perturbation method, you have to also expand the velocity of the Stokes waves to knock out secular terms when you're calculating the corrections to these Stokes waves. And that's it. I won't go through the gory details of all of it. It's not a hard computation to do, but it is very tedious. And certainly, if you are trying to compare these asymptotic expansions to numerical results, there are always speed bumps that happen along the way. And so once you get over those speed bumps, once you smooth them out a little bit, this Stokes wave computation is very classic, very well known, and you can get a symbolic algebra package to calculate what these corrections are for you. And so that's what we do in our analysis, and we take these expansions out to 4th order. I would encourage you as a homework exercise, for those that really want to, you could take it out to 5th, 6th, 7th order if you want to. But I'm going to tell you right now, doing it by hand is probably not the best way to do it. You're going to want to stick with something like Mathematica or Maple to help you out. Once you have these Stokes waves, or at least an asymptotic expansion for these Stokes waves, now you're ready to talk about the stability spectrum. So what we're going to do is we're going to take a Stokes wave and we're going to perturb it by a function that's a bounded function on the whole real line. And so one can show that the normal modes of these types of perturbations are functions that have exponential time dependence, where lambda here is going to control the growth rate of these dependents. And then we have some oscillatory behavior that's happening in space. In particular, we have this complex exponential factor, which introduces this parameter mu. Mu is called the Floquet exponent. It's something that you're free to choose without loss of generality. You can choose it between -1/2 and 1/2. And this mu parameter is essentially characterizing the degree of quasi-periodicity of this bounded function on the whole real line. If mu is a rational number, then you're really truly going to have some sort of periodic function that you're perturbing your Stokes waves with. If mu is an irrational number, then you get some sort of quasi-periodic function that you are perturbing your Stokes waves by. So that's that complex exponential piece. It's coming straight from Floquet's theorem, which is why this parameter mu is called the Floquet exponent. And then there are these functions n of x and q of x. These are truly periodic functions that happen to have the same period as our Stokes waves. And since our Stokes waves are 2 pi periodic, these functions n of x and q of x are also going to be 2 pi periodic, and as smooth as necessary. They're in whatever function space we can think of to make this problem work for us. And so this is how we're going to perturb our Stokes waves. We take this expansion, which is in the rho variable right now, and we plug it into Euler's equations. And at order rho, we end up finding a spectral problem. And the eigenvalues of this spectral problem are exactly the lambda parameters that give us the exponential growth rates of these perturbations. And so the values of these lambdas, those were what was in that plot that I had shown you several slides back in the stability spectrum. But those were, of course, computed numerically. What we'd like to do is compute them asymptotically. And so here's going to be the idea. We have these linear operators, L and R. They're very complicated. They are 2 by 2 matrix integro differential operators. They operate in very, very special function spaces. And the important takeaway from these operators is not explicitly what they look like, but what they depend on. And these operators both depend on a small parameter epsilon that encapsulates the amplitude of our Stokes wave. And they also depend on the Floquet exponent mu, which is describing for us exactly what types of perturbations we want to apply to these Stokes waves. And the important thing about this spectral problem is that when you set epsilon to 0, we can solve this problem exactly. Because when epsilon is 0, this operator R and this operator L become constant coefficient. And it turns out that your eigenfunctions are just Fourier modes. And once you know what the eigenfunctions are, you can easily from this equation back out what the eigenvalues have to be. And so when you set epsilon to 0, you can calculate these eigenvalues exactly, and you find that they're all purely imaginary. And hopefully that shouldn't be so surprising, because when epsilon is 0, we're talking about a Stokes wave that has no amplitude, i.e. we're talking about flat water. And flat water, you would hope, is a spectrally stable solution to the Euler equations. If it wasn't, then you'd have a whole other interesting problem to look at. So we have all of these eigenvalues. They're all purely imaginary. And it turns out we know a little bit more than this. It turns out that peppered onto this imaginary axis are a countably infinite number of repeated eigenvalues. Okay, there's the one that's at the origin, which ends up having algebraic multiplicity 4. And then there are these eigenvalues that are repeated away from the origin that have algebraic multiplicity 2. And what happens when you turn on the epsilon parameter here to these repeated eigenvalues is a Hamiltonian Hopf bifurcation. And so essentially, these repeated eigenvalues that are sitting on top of each other in the epsilon equals 0 spectrum, they split up. And because of the symmetry that this spectral problem has, due to the fact that the Euler equations are Hamiltonian, you can show that one of these eigenvalues in this pair that's going to split off the imaginary axis has to enter the right half complex plane and has to give us these instabilities. And so this is how we get that famous picture that I had shown you numerically a few slides back. They come from repeated eigenvalues in the epsilon equals 0 spectrum. So now what I'm going to do is I'm basically going to introduce a perturbation method that selects one of these repeated eigenvalues and then turns on the epsilon parameter, and through using perturbation methods, extracts the unstable eigenvalues in the small epsilon case that were nearby to that repeated eigenvalue in the epsilon equals 0 case. And in particular, to sort of ground our analysis here, I'm going to pick the first high frequency instability bubble close to the origin. So that's going to be this repeated eigenvalue that I've assigned to the value p equals -2. And we're going to track what happens to the unstable eigenvalues that emanate from that particular repeated eigenvalue. We could have also picked p equals 2. Again, there's a symmetry in this spectrum. So if you focused on this particular repeated eigenvalue that's close to the origin, you would get the same results. Nothing would really change. And the reason why I'm choosing to pick these particular repeated eigenvalues, as opposed to any of the other eigenvalues that you see on this imaginary axis, is because this integer p is going to have a physical interpretation that you're going to see later on in the calculation. And the current conjecture is whatever the value of this integer p, its absolute value tells you how far out in the asymptotic expansion you need to go to find these high frequency instability bubbles. And so for the case of p equals -2 or p equals 2, we're only going to have to go out to second order to find these high frequency instabilities. Whereas if I chose p to be 10, you would have to sit here and watch me go through 10 orders of perturbation theory, which I don't think any of you really want to do unless you really, really love perturbation methods. So I'll spare you from doing that. Let's do the simplest possible case and choose the repeated eigenvalue that's closest to the origin. And you will see throughout the calculation that once I get to second order, I will be able to get a leading order approximation to these unstable eigenvalues on that high frequency instability. And if there's time at the end, which I'm not so sure looking at the clock now we'll get to, we can talk about what happens at the origin, and we can focus in on what happens with the Benjamin-Feir instability in particular. So let's go ahead and set up our perturbation method. The idea is we choose one of these integers p to focus in on. And in particular, we're going to focus in on the case when p is equal to 2, which is that high frequency instability that's closest to the origin. We can immediately, from choosing that particular repeated eigenvalue, back out what the Floquet exponent that corresponds to that eigenvalue is. We can back out what the expression for that eigenvalue is, and we can back out an expression for the eigenfunction. And it should be no surprise when you're looking at the expansion of this eigenfunction that there's really two linearly independent directions to this eigenfunction. That's because the repeated eigenvalue that we're expanding around has algebraic multiplicity 2, and it turns out that it also has geometric multiplicity 2. So you end up getting these two independent directions. And if you look at the Fourier modes that are involved in these independent directions, specifically looking at the wave numbers, you'll notice this wave number here is n, this wave number here is n plus p. The key observation is that the difference between those wave numbers is exactly this integer p. And so that's the physical interpretation of that integer. When you select your repeated eigenvalue, whatever the value of that p is telling you the difference in the wave numbers of the two independent directions in your eigenbasis corresponding to that repeated eigenvalue. So this is all well and good. You've got your Floquet exponent, you've got your eigenvalue, you've got your eigenfunction, which is written as a sum essentially of two different Fourier modes that are sort of resonating with each other. And now for the formal step. Now we're going to expand around these particular eigenvalues. And in particular, we're going to assume formally that we can expand as a power series in epsilon. Now, before the rigorous results came out from Berti et al., from Her and Young, from Wynn and Strauss, this was a 100% formal assumption. But that doesn't mean that it's not a careful assumption. This assumption comes directly from numerical simulations and what they suggest. And it also comes from the long-standing principle that you should always follow with perturbation methods, which is to try the simplest thing possible first, which is a power series expansion, and hope that you get something that is self-consistent versus having to make your life complicated initially by changing what these gauge functions are and then figuring out what they are later. So really, when we did these expansions, we were led by numerics and trying the simplest thing possible. And luckily for us, we're going to find that these expansions actually work. And not only do they work exceptionally well when you compare them to numerical experiments. So that's what we're going to do. We're going to take this eigenvalue, this eigenfunction, and importantly, this Floquet exponent, and expand it as a power series in epsilon. Now, before we go through the tedium of the actual perturbation method that we just set up, allow me to make one extra comment about that Floquet exponent parameter. Because if you'll remember, we already fixed that Floquet exponent to correspond to whatever the repeated eigenvalue was in our epsilon equals 0 spectrum. And so one would be led to believe that in this perturbation calculation, that Floquet exponent should always be fixed to be whatever the repeated eigenvalue, whatever the Floquet exponent of that repeated eigenvalue was. But it turns out that that is an egregious error, unfortunately. What you're seeing in this plot on the left is a plot of the first high frequency instability bubble closest to the origin for various values of epsilon. When epsilon equals 0, we don't really have a bubble of instability yet. We just have this repeated eigenvalue at this gold star. When you turn on this epsilon parameter, you can see that the bubble is created and the width of this bubble is getting larger with epsilon. And this bubble is drifting along the imaginary axis. And actually, it's drifting like order epsilon squared, it turns out. So that's what's happening in our stability spectrum. But if you go to Floquet space, here's what's really happening. On the x-axis here, we have our different values for the wave amplitude of our Stokes wave epsilon. And on the y-axis, what you're looking at is the interval of Floquet exponents that are parameterizing these high frequency instability bubbles that you see on the right, or excuse me, see on the left. And what I want you to notice is that if you fix the Floquet exponent to correspond to the repeated eigenvalue, that's fixing your Floquet exponent to be what the value of this gold star value is. Here I've sort of subtracted out the mu naught value on the y-axis just to show a sense of order of magnitude up here. But right at this point 0, 0, that corresponds to the Floquet exponent mu naught. And if you fix that value, what you're going to notice is that that value is never in the interval that parameterizes your high frequency instability for any small value of epsilon, because this interval moves away from that particular Floquet exponent. And it moves away actually like order epsilon squared, as we will see when we do the actual computations. So the mistake that you would make by fixing the Floquet exponent to be what the repeated eigenvalue tells you is that you may not even capture the high frequency instability bubbles at all. You could completely miss them. So it's very important that this Floquet exponent also be expanded as a function in epsilon as well. All right, now for the tedious part. We have these expansions for our different spectral properties. We plug all of those expansions into the spectral stability problem, collect powers of epsilon, and essentially we're going to create a sequence of linear problems that we have to solve. And each one of those linear equations is going to have with it certain solvability conditions that have to be satisfied in order to solve those linear problems. And it turns out that when you look at the order epsilon problem from this perturbation expansion, you find that the solvability criterion tell you that your first order correction to your eigenvalue is 0. And that's also true for your first order correction to your Floquet exponent. And this is a bit of a heartbreaking result because up to this point, you've done so much algebra, you worked very, very hard, only to find that you get zeros at this first order. And this also tells you the crushing reality that you have to go to the next order if you really want to get what you're after. So we go to the next order. And luckily at the next order in this perturbation problem, you get something non-trivial for the second order eigenvalue correction. And in fact, this expression is really, really non-trivial. And I'm kind of masking how difficult this expression is by introducing some intermediate variables. So the S variables that you see here, they are actually explicit real valued functions of the dimensionless depth parameter alpha. And these C variables are actually explicit real valued functions of the dimensionless depth parameter, as well as the second order Floquet correction. And they're very complicated. So this expression, while it looks simple, is actually not. It's a very complicated expression involving the depth and involving the second order Floquet correction. Now, when we're looking at this second order correction, what we're hoping to find here is a real part correction. And this first piece is not going to do it for me. That's purely imaginary. But this second piece with the radical in it, maybe there's some hope here. When you first look at it, maybe there's not so much hope because we can see that this first term is negative definite, so that's not great. And the second term has a negative sign in front of it, so who knows whether it's positive or negative. But this is where a minor miracle occurs. You can show actually that these two S functions, when they multiply together, equals the negative of some new function, which I'm calling S2 of alpha, squared. So actually this second term is positive. And that gives me hope that maybe I can make the stuff underneath the radical positive to give me a real part correction to this lambda 2, which in turn is going to give me the first correction to this high frequency instability bubble. Now, the only thing that could rain on our parade here is if this S2 of alpha function just so happened to identically vanish for all alpha. And so at this point, we need to do some analysis. Or rather, maybe you guys need to do some analysis. This is what the expression for S2 of alpha looks like. It's pretty gnarly. Good luck trying to get any analytical results out of this function. There's transcendental functions in here galore. Lots of tangents, seches, square roots everywhere. It's a mess. And to make matters worse, this really isn't the full story of this S2 of alpha function. There's actually another parameter that's in this expression for S2 of alpha, and it's a solution of an implicit transcendental equation that has alpha as a parameter in that equation. So first, you have to solve that implicit transcendental equation for that variable, and then you could plug that variable into this expression, and then you could analyze S2 of alpha. So the conclusion here, I hope, is that you trust me and that S2 of alpha is very complicated, and that getting an analytical result out of S2 of alpha is going to require an extreme feat of analysis. So what are we going to do instead? So what we're going to do instead is actually plot what S2 of alpha looks like. And if you do that, and I'm realizing that I deleted that slide, unfortunately, for whatever reason, you will find that S2 of alpha does not vanish for any value of alpha except one special value equal to 1.84, et cetera, et cetera. And it turns out, because S2 of alpha is, for the most part, except for that one special value, not 0, you can always arrange what's underneath this square root to be a positive number by picking your Floquet exponent mu2 in just the right way. And this is going to give you your high frequency instability bubble. So what we're really saying here is, in almost all depths, except in that special case where alpha is equal to 1.84, et cetera, et cetera, et cetera, except in that one special case, you will always have a high frequency instability bubble in your stability spectrum. And so your Stokes waves for almost all depths are unstable. Now, what happens at that special value of alpha where this S2 of alpha parameter vanishes? That's an open problem. It's not clear yet whether the high frequency instability bubble really vanishes at that particular value of alpha, or whether you need to go out to higher order and see what happens at third and fourth order for that particular value of alpha, and see whether you get a real part correction later on in the asymptotic expansion. It's not at all obvious. And if you're sufficiently intrigued by this expression for S2 of alpha, maybe you might consider answering that question. Okay, this slide here is just summarizing everything that I just said in words. All we're doing is enforcing what's underneath the square root to be positive. And when we do this, that puts a restriction on our second Floquet correction. This second Floquet correction can be any number you like, provided that this inequality is satisfied. And so this mu2 parameter is the free parameter that actually parameterizes the high frequency instability bubbles. And that really concludes the perturbation method. That's the major ideas. So how well does it work? So that's what I'm going to show you in the last 10 minutes here, some pretty pictures. So what you're looking at in the figure on the left is the first high frequency instability bubble closest to the origin. The solid red curve is the asymptotic prediction. The blue dots are numerical methods using the Floquet-Fourier-Hill method. And here we're talking about a Stokes wave with amplitude 10 to the minus third, and we're talking about a depth equal to 1.5. And you can see the agreement is excellent. On the figure on the right, we're looking at the Floquet parameterization of the figure on the left. In particular, in blue, you're looking at the real part of the eigenvalues on our bubble as a function of the Floquet exponent. And in red, you're looking at the imaginary component of this bubble as a function of the Floquet exponent. The dots are numerical results, and the solid curves are what these asymptotic computations predict. And again, we see excellent agreement here. If you wanted to look how these quantities depend on epsilon, what you could do is plot, for example, what does the interval of Floquet exponents look like that parameterizes this high frequency instability as a function of epsilon. And in the solid curves, what you're seeing are asymptotic predictions. And in the dots, you're seeing numerical results. Again, excellent agreement. This red curve, by the way, that you're seeing in the middle here, that's the Floquet exponent that corresponds to the most unstable eigenvalue on this asymptotic curve, essentially. And it turns out that, at least to leading order approximation, that curve is right in the midpoint of this interval. But higher order corrections, of course, take you away from the midpoint. And you can calculate those corrections if you want. That'll be a little bonus problem for after this talk, if you want to do that. What you're looking at in the figure on the right in blue is the real part of the most unstable eigenvalue as a function of epsilon, and the imaginary component in red as a function of epsilon, of that most unstable eigenvalue. Again, the dots are numerical results and the curves are asymptotic results. So it looks like things are working quite well for us. Let's talk about infinite depth, because everything that I've shown you so far is only finite depth. And it turns out in infinite depth, the perturbation method works just the same way. Virtually no differences, with one exception. And that is when you look at this high frequency instability bubble that we've calculated in infinite depth, and you look at the value of epsilon that we're using here, which is 10 to the minus second in this infinite depth, and you look at the x and y axes and see what the scaling is here, you're going to realize, hopefully pretty quickly, that this bubble is not on the order of epsilon squared like it was in finite depth, but on the order of epsilon to the fourth. And so here's an interesting remark about infinite depth. A lot of people are under the impression that infinite depth is easier because you don't have the depth parameter to worry about. But it turns out in this case, when you're working with high frequency instability bubbles, there's a price to be paid for having simpler asymptotic expansions. And that is, in infinite depth, you have to go out 2 orders of magnitude more in epsilon to find this first high frequency instability bubble. So as Bernard likes to tell me often, there's never any free lunches. And in this case, infinite depth is not a free lunch. You get a simpler asymptotic expansion, but you have to go out further to get what you want. But nonetheless, if you're willing to hoof it all the way out to order epsilon to the fourth and deal with all the tediousness that comes with, you will find that this perturbation method works fantastically well. What about if you focused on a different high frequency instability bubble? So these results that you're looking at here are for the p equals 3 high frequency instability. This corresponds to the second closest high frequency instability to the origin. When p equals 3, it turns out you have to go out to order epsilon cubed to calculate what that high frequency instability bubble looks like asymptotically. And that's actually what you find in the dashed curves. So the dashed curves give you the order epsilon cubed result. What's interesting about this instability is that you actually have to go out one order higher because there's a very large imaginary correction that happens. And so if you go out to order epsilon to the fourth with these instabilities, then you get what's in the solid curves. And then you get excellent agreement again. And I should say that it's not fair of me to say that the dashed curves are really a bad fit here. That's partly a choice of how I chose to scale the axes. The dashed curve and the blue dots are close together, but the error here is on the order of 10 to the minus 7. And that 10 to the minus 7th term is taken into account when you go to the next order. So it's not like the perturbation method fails at order epsilon cubed. You just have to keep going because there's a correction that happens at the next order that's relatively large. So that's one of the interesting properties of these instabilities further away from the origin. You've got to go out to very high order, and sometimes you might have to go out even one order further because there might be very large imaginary corrections that shift sort of where the center of that high frequency instability bubble is. And now I think I have 5 minutes left. I'm going to be very terse with this last section, but it would be a shame of me not to show you how you could at least modify this method to make the Benjamin-Feir instability work. So let me just very quickly just describe at a high level how you get this method to work for Benjamin-Feir instability. The main idea is the same. You have a repeated eigenvalue at the origin. So lambda naught is 0. Its corresponding Floquet exponent turns out to be 0. And it turns out, as we saw in the previous 2 lectures, that particular eigenvalue has an algebraic multiplicity of 4 and a geometric multiplicity of 3. And here are your 3 linearly independent directions for your 0th order eigen function correction. Once you've got the 0th order stuff, basically you can expand your lambda and your eigenfunction just as you did before as power series in epsilon, which again is a formal assumption that's now backed up by the rigorous results of Berti et al. And there's one other thing that you have to pay attention to, which is that your expansion for your Floquet exponent mu is going to be slightly different for the Benjamin-Feir instability. And the reason for this is because the Benjamin-Feir instability, the interval of Floquet exponents that parameterize that figure 8 curve have to be symmetric about the origin in Floquet space. And this expansion right here enforces that constraint. Mu0 here obviously is 0. Epsilon mu1, this mu1 is going to turn out to be a free parameter that's going to be in a nice symmetric interval. And what we want to do after we have that symmetric interval is just take that interval and modify its width. And that's what this factor of 1 plus r of epsilon is going to do. It's going to magnify this width of this symmetric interval. So the Floquet expansion is a little different than the high frequency instability bubbles, precisely because the high frequency instability bubbles don't need this extra constraint that their intervals of Floquet exponents have to be symmetric about the origin. But for Benjamin-Feir, it does. So you have to modify the method right here at this level. But after that, after you take that into account, it's the same thing as it was before. You start going through the perturbation method. You find at leading order, you get a purely imaginary correction for your eigenvalues. And then you go through these crazy solvability conditions, and you find out that this is your second order correction to your eigenvalue. It's got an imaginary component. And then it turns out that there's this real component. And this component is real precisely when your depth is bigger than 1.363. And this figure, yes, is almost an exact carbon copy of what we saw 2 video lectures ago. In fact, it's the same thing. This quantity that we compute here is the leading order correction to the Berti et al. Result. So this is a very nice connection piece from a formal asymptotic perspective, where we're covering exactly what we were hoping to find from a rigorous standpoint. I'll skip this piece because there are some subtleties that are involved in the perturbation method that require thinking about this R1 parameter, which at second order is not determined. So you have to do something special there. And maybe one of your questions might be what that special thing is. So maybe I'll save that for you to ask me in the next 10 minutes here. Let me just show you the results numerically, just so you convince yourself that indeed this perturbation method is going to work just fine for the Benjamin-Feir instability. And so the blue dots here are numerical results, and the solid curves are the leading order approximation to that Benjamin-Feir figure 8 curve. And the figure on the right is the Floquet parameterization of the real component of this curve and the imaginary component of this curve. The dots are all numerical results, and the curves themselves are actually the asymptotic results. And in fact, if you want to get even better results, you can push this to higher order, which is what we've done in, Bernard and I have done in our most recent paper together, which was just published this year in JFM. And you'll see that this green curve is the higher order approximation. This orange curve was the first order approximation. So in fact, if you're willing to put in a little bit more effort into the perturbation method, you will get an even better approximation, just like you hope you could do. And so this is the last slide that I'll show, and I'll wrap it up here. So this particular slide is showing you what the interval of Floquet exponents looks like for the Benjamin-Feir instability. Here I'm only showing half of that interval. So there's another half here that goes into negative mu values because there has to be a symmetry here. And the dotted curves that you see here correspond to numerics, and the solid curves correspond to the asymptotic results. In fact, the light blue here and the dark red here, those are curves coming from the higher order asymptotic results. So the perturbation method is working extremely, extremely well. And they work in infinite depth as well. So just to summarize, these perturbation methods, they're relatively simple-minded. They're relatively elementary to do. You start with your repeated eigenvalue and your epsilon equals 0 spectrum. You expand these guys. For Benjamin-Feir, you have to be a little bit careful how you expand that Floquet exponent. But otherwise, you turn this into a regular perturbation theory problem. And the current conjecture that has yet to be proven is that the first real part correction for your eigenvalue happens at order epsilon to the p for a high frequency instability that corresponds to that integer p. And of course, for the Benjamin-Feir instability, you get your first real part correction at order epsilon squared, which is what has allowed everyone to sort of get these rigorous results. You don't have to go too far in epsilon. But this is a big conjecture. We have no idea how to solve it. Once you've gotten past that order and you've gotten your leading order correction to these high frequency instabilities and to the Benjamin-Feir instability, you can keep going with this method. But like I said, there are certain things that you have to take into account at these high orders that allow you to uniquely determine the next order corrections to these eigenvalues and Floquet exponents. And like I said, I will leave that for a question that you could ask me, or we could just leave it at that. But that's the perturbation method in a nutshell. And with that, I thank you so much for your attention, and I'll take any questions that you may have.
All right, thank you, Ryan. I think we have plenty of time for questions.